You know, scrolling really slow today. This might help. All right. Welcome back, everyone. A couple of things we want to point out. Remember that we did say our test 3 was going to be on the 9th and 10th. Let me just put this on another document really quickly. And that will be on chapter 7 and 11. The review is available in my math lab now. And I have also updated the homework dates. If any of you realized, I had the 11.1 homework date set for, I think, November 30th, and I've made that the actual date, which it should be, which is December, what, 7th? December 7th, sounds right. And then we'll finish 11.2 today, so that I'll be doing the 9th. I'm hoping we also finish 11.3 today, so that you do get your full week of studying with that. After test 3, and it's the usual, you have work to submit in Canvas, but you are allowed a calculator. But remember that I do reserve the right to go and look at your work, and if I don't see any work, I can go back and take away all of your points, even if you have right answers. And I would only do that on complicated questions. If it's something like a vector problem with 1 or 2 steps, I'm not going to take points away from something like that. I'm talking about you had a triangle problem to solve where there was no right angle, and you're supposed to be doing law of sines and cosines and seeing if there's 2 triangles and all that different jazz. That's the type of problem where if I see a correct answer but no work for it, then I'm going to take away all your credit because clearly you pulled this answer out of thin air, and we all know what thin air means. Finally, the final exam, which is cumulative. This is 1 day only. This will be Monday, December, is it 14th? Yes. Calculator is okay once again. It will be of a similar length to the previous tests, you know, somewhere in the ballpark of 20 to 25 questions with a 2-hour time limit. You'll have to submit your work in Canvas. I don't think I need to explain all those finer details, but there is no class the day of the final or after. So our last class meeting is December 9th. So including today, we're only going to be talking and discussing for 3 more days. So this Wednesday, then Monday the 7th, and Monday the 9th, and that is it. So again, on the 14th, you are responsible for doing your final, and since I can only give you 1 day for the final, it's all I can allow, I want to make sure that if you need to use the class time, that you have that available. That's why I'm not going to be lecturing, and it's exam week. Who lectures during an exam week? And then the 16th, we're just done at that point. So if you have any questions about this stuff, please email me. Besides that, let's go ahead and let me just do this. Let's go ahead and continue where we left off in 11.2. So 11.2, we introduced the arithmetic sequence, which we said arithmetic sequence just is a fancy way of saying that the new term is the previous term plus a number, and that number is always the same. So to get the 10th term, if you add 17, to get the 11th term, you add 17. To get the 12th term, you add 17. To get the millionth term, you add 17 from the term previously. And we developed a formula or 2 for these that we said, while you can blatantly memorize the formula, there's logic and reasoning to them. We said if you just need to find a particular term of a sequence, just take the first term and add that common difference 1 less time than the number of terms you're trying to get to. And we also said that if you want to find the sum of the first n terms, I terms, whatever, where did it go? Here we are. That you could just average the first and last term, that's the A1 plus the A2 divided by 2, and multiply by the number of terms. So I have that in words here. I've got a formula here. Memorize the formula or understand the concept. We discussed why it works. We didn't do a formal proof, but I did give you kind of a basic idea of it, why it works, how you can just shift values from one number to another number and they always become symmetric to each other. But we did say that if you want to use the arithmetic sequence, you have to either be told it's arithmetic or you have to prove it's arithmetic. The proof of something being arithmetic just means find a couple terms and show that the difference between the terms is always the same, as we saw in example 3a. So we'll pick up where we left off, which is example 3b. Let's do this so you don't see too much. Avert thine eyes. Actually, we'll do it up here. Here we go. So this says, for example 3b, we're going to find the sum of the first 100 terms of the sequence I. So if your sequence is I, that just means the first term is 1, the second term is 2, the third term is 3, the fourth term is 4, the fifth term is 5, the 99th term is 99, and the 100th term is 100. So what we have written here is just a fancy way of saying, find the sum of the first 100 numbers. Now, sure, you could go 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7 plus 8 plus 9 plus 10 plus 11 plus 12 plus da 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 da. If you type it in a calculator, someone's going to butterfinger that and they're going to get an error. If you try and do that in your head, you're going to have to be really good with numbers to get that right in your head. I can't even handle that far. In addition, honestly, I can add quite a few numbers. I'm pretty good with numbers, but I can't go that far. So what we do is we want to show that this is an arithmetic sequence so we can just really easily do the first term, the last term, and then that quick little formula. So let's show it's arithmetic by finding the first, second, and third terms at a minimum. If you want to find the fourth term, that would really confirm it, but it's not necessary for the problems we'll do in here. So to show it's arithmetic, you find the first term, which is 1. You just plug in the 1. There's nothing else to do to it. It's just 1. And you might see a detail up here that you shouldn't see yet. There we go. Then let's find the second term, which is 2. The third term would be 3. The fourth term is 4. The difference between the first and second term is 1. The difference between the second and third term is 1. If you keep going, the difference between the third and the fourth term is 1 because it just keeps incrementing by 1. So that means it's arithmetic with a common difference of 1. So I'm going to go on mute for a second. All right, so we have established that this is arithmetic, which means all we need is the first and last term. Well, the last term is really easy to find out. It's just 100. Now I said, if this was like a recursive formula or some crazy formula, you could just take the first term and add that common difference 99 times, because to get to the 100th term, you're only going to add it 99 times, and 1 plus 99, because that's 99 times 1, is 100. So there is 2 ways that we could achieve that 100th term. Now all we're going to do is average these 2 terms, so we'll add them and divide by 2, and then we multiply by the number of terms. So the sum of the first 100 terms of the sequence I, aka this notation is just S sub 100. And I'll admit, no one really uses this notation too much in crazier calculus classes, but it is still valid. So that is the number of terms 100. We're using, again, this green formula right here. So the n is the 100, but I don't put my over 2 there. I put it under the parentheses because I prefer the concept of take the number of terms times the average. Oops. So here's the n, the 100. The over 2 I just put with the parentheses instead. And here is me averaging the first and last term, 1 plus 100 over 2, which would be 101 over 2. So you're doing 100 times 101 and dividing it by 2. But you could actually divide first. Half of 100 is 50. That's a lot easier to half because they divide evenly. So we're just doing 50 times 101. If you plug that in the calculator, 50 times 101 would be 5,050. So the sum of the first 100 integers, or the 100 whole numbers, is 50-50. Are you sure about that? Well, I'm 50-50. Sorry, horrible joke. I'm going to math heck for that. All right. But that is definitely shorter and easier than going in your calculator and literally typing 1 plus 2 plus 3 plus 4 plus 5 plus 99 plus 100. Especially because if you're anything like me, you're going to make an error somewhere, and you're probably just going to be hyper fixated on continuing the addition chain, and all of a sudden this addition comes up to 5,040 or 50,000 something, or I don't even know. Last problem of the section. Told you there wasn't very much left in the section. What the information we're given tells us is that we have a sequence where the first term is -42. We're told the common difference is 7, which means to get the second term, add 7. To get the third term, add another 7. To get the fourth term, add another 7. And we want to find the sum of the first 66 terms. That's what that information says in front of us. Now this time, unlike A and B, we don't have to show that it's an arithmetic sequence. We were told it's an arithmetic sequence by having been given the D. So we want to find what -42 plus -35 plus -28 plus -21 plus -14 plus -7 plus 0 plus 7 plus 14 plus, and there'll be 66 of those terms. Once again, trust me, you don't want to put that in your calculator. It is much easier to have the first term, find the last term, average them, and then multiply by the number of terms. Or just use the formula as you blatantly memorize if that's what you're doing. Now, I did not give you the formula to find any particular term of the sequence. If I want to find a sub 4, I might need to find a sub 2 and 3 to find it. But we don't actually need to do that, especially with 66 terms. You don't want to have to find the first 65 terms to find the 66th term. There's a way to shortcut this, and that's because since we just keep adding that same number over and over and over and over, let's just take the first term, add that D one less time than the term we want to find, and boom, we'll have the term. So if we want the 66th term, we're just adding 7 65 times. Now again, if you're using the formula, this is what it looks like. And I didn't show the 66 minus 1 part, but that's what this would have been before. So here's your first term. I'll remind you what the formula is up here. Your first term plus 1 less than the terms you're finding, because that's how many times you'll add the D, times the D. Where are we? Here we go. All right, so 65 times 7, if you jam that in a calculator, is going to become 455. And then -2 plus 455 is going to be, what's that, 413? Yes, 413. So that's your 66th term. That's your last term of the sequence that we were asked about. So now, either the blatantly memorized formula or the concept. I like the concept, so I go the number of terms times the average of the first and last term. If you like the formula, here's the formula that you're memorizing. You're not writing down for tests, you're memorizing this. So here's our formula. And again, this is my version where I take the number of terms, 66, times the average of the first and last. So -42 plus 413 over 2. -42 plus 413 is 371. I also did the 66 divided by 2, which is this 33. So I did 2 steps in one. I hope that doesn't throw you off. And the 2 goes into 66 33 times. Then this sum in the parentheses is the 371. And if you plug that in a calculator, which I remind you, you are allowed for this section, for this test, you get 12,243. Arithmetic sequences are awesome. They're seen all over the world. They're seen in math, all over the place. Obviously, that's what I meant by all over the world. But they are not the end-all be-all. Arithmetic sequences are ones in which, to find the next term, you take the previous term and add something, where that adding something is always the same. So if you add 5 to go from the 1st to the 2nd, you're adding 5 to go from the 10th to the 11th, you're adding 5 to go from the 55th to the 56th, you're adding 5 to go from the millionth to the millionth and first. And with that simple concept, we get two pretty easy formulas involved with them. But quite honestly, while there are a lot of things in the real world where you have a sequence of something and it's just to keep adding the same thing over and over and over, it's also pretty common in the real world to have what we call a geometric sequence or geometric series, where each term is a constant multiplier of the previous term. So to go from the first term to the second term, you multiply by 3. To get the second term to the third term, you multiply by 3. To go from the 5th term to the 6th term, you multiply by 3. To go from the 100th to the 101st term, you multiply by 3. Your finances, if you are investing or even if you're just in putting your money in a savings account, that's essentially a geometric sequence or a geometric series. I mean, not a series. You can argue it either way. Most people treat it as a sequence, but you can treat it as a series as well. It's just kookier. Because your savings account, you gain a certain percent every year, and it's a multiplier. If you gain 3%, then your new amount of money is 1.03 times your old amount of money. The 1 being what you originally had, the 0.03 being the 3% that you gained over the year. And then if your interest rate never changes, to get the next year, you multiply by 1.03. To get the year after that, you multiply by 1.03. Or you can treat it as a series where you just take the 0.03 times the base to get the interest. Then the next one is 0.03 times the previous, and et cetera, and just add everything. Again, you can treat things as sequences or series quite often. So a geometric sequence or series is one in which the next term is found by multiplying the previous term by a constant. We give this number a name. For the arithmetic series, we called it the common difference. Now we call it the common ratio. Common ratio, constant ratio, those are interchangeable words. We call it a ratio because it's literally the next term divided by the previous term to find that number. So if, let's say year 1, you have $1, year 2, you have $5, year 3, you have $25. To find your multiplier, you just take the 5 divided by the 1, or the 25 divided by the 5, or the next one would be 125 divided by 25. You're just dividing the newest and the previous. Previous, I don't know why I put an ST in there, previous. So the common difference was literally the difference of the next and the last term. The common ratio or constant ratio is the ratio, the division of those two things. And of course, we can develop and use formulas to find the sum of maybe the first 10 or 12 or 200 terms. We can have formulas to find the 12th or the 200th term. And in fact, under certain conditions, we have formulas to add up infinitely many terms in this type of series. But there's conditions. And those conditions are going to continue through Calc 2 over and over and over. Again, I've really tried to hammer out that this stuff in Chapter 11 will be seen again, and specifically, it's the geometric sequences and series that we really focus on in Calc 2 and beyond. All right, so really quickly, just kind of going through a proof, and again, I do mean really quickly due to time constraints. How can we develop a formula to find some random term? And I don't mean random, but like they tell us to find the 66th term. What's the formula for it? Well, let's develop it. So if I give you the first term, which you have to be given, and the constant multiplier, the constant ratio, the common ratio, whatever you want to call it, the thing you're multiplying the last term by to get to the next term. All right, so what's the second term? The second term is going to be, well, you take the first term times r. So if your first term is 1 and your multiplier is 5, 1 times 5 would be 5. And there's nothing really to do there, so I just have A1R listed again, because the rest of them, I will be changing things. So the second term is just the first term times r. That's the entire concept. But continuing this, what would the third term be? Well, the third term would be the second term times r. And you'll notice I've got some red stuff underlined, and that's because they're the same thing. The second term, we just said, is actually the first term times r. So this little a sub 2, I'm going to replace as a sub 1 times r. Now be careful, there's this r here. This r is not the same as this r. They're the same value, but they're different r's. There's two of them. So I even use red ink to emphasize that this right here, this a2 is this a1 times r, because the second term we said was the first term times r. So instead of writing the second term, I write the first term times r, but there's that extra r multiplying it, and r times r is r squared. And have a little green squiggly under it because we're going to end up using that. And we're just going to keep cycling through this. So what's our fourth term? Our fourth term would be the third term times r. But we just said what the third term was. The third term is a1 times r squared. So in green, I'll write what a3 is over here. So there is the third term. But then we have that extra r we're multiplying by. And r squared times r is r cubed. So the fourth term is just the first term times r to the third. The third term is the first term times r to the second. The second term is the first term times r. Do we see a pattern yet? The last term is just the first term times r to one less power. It's actually coincidental there. And it makes sense that you're going to multiply one less time in the same way that with the arithmetic sequence, we added it one less time. Because the first term doesn't involve the r at all. It's when you get the second term, we start adding something or multiplying something. So if you follow the pattern, in general, we can say that any nth term is just the first term times r to the n minus 1. So we're multiplying by that common ratio, that constant ratio, one less time than what we're trying to get to. So here's a formula that you can memorize, or quite honestly, if you ever forget it, you can develop it. But again, it makes sense. The way I think about this is that any term is the first term times the multiplier one less time. So let's try using it. Let's find the seventh term in the geometric sequence where your first term is 2 and that constant multiplier is 3. So we're tripling every time we go through a value then. Maybe this is us saying we're tripling our money every year, which means we're doing really good as an investor. If you're tripling your money every year, please email me and tell me some financial advice, right? Sarcasm there. Kinda. You're tripling your money every year. I need to know what's up. All right, so find the seventh term in the sequence. Now, sure, we could find the second term by taking 2 times 3, which is 6. We could find the third term by taking 6 times 3, which is 18. We can find the next term by taking 18 times 3, which is 54. And I'm already losing track of which term I'm at in my head because I'm going really quickly. Imagine we wanted the 70th term or the 700th term or the 7 millionth term. You don't want all those middle entries, though. If you have a shortcut, which we do in blue ink here, you need to take that shortcut. So we can find the 7th term by taking the first term and multiplying it by the multiplier only 6 times. So the 7th term would be the first term times the multiplier raised to the 6th power. And then we can just jam numbers into this. If you don't write the formula out first, if you go ahead and write it straight with numbers, that's fine too. It would be 2 times 3 to the 6th, because the first term is 2. We're multiplying by 3 6 times to go from the first term to the 7th term. Now, please remember 2 times 3 to the 6th, you cannot take the 2 times 3 and call that 6 to the 6th. PEMDAS does not work that way. You have to do the exponential part first, then double it. 3 to the 6 turns out to be 729. Please show that in your own calculator. And then 2 times 729 would be 1458. That is a ridiculously easy thing to do. I'm not going to do multiple examples of it because of that. We're just sticking to brass tacks. I was talking to someone the other day, they thought the phrase meant TAX as in like the tax you pay, but no, it's TACKS, brass tacks, an actual physical object. Not that that is relevant, but I'm a little, I like mentioning things, that's all I'll say. All right, to find the sum of a geometric series. So we know how to find any particular term of a geometric series. We're going to give you a formula. And here it is. And once again, you can memorize it. And quite honestly, you really are just going to have to memorize it. There's no good logic to this one. But at least there's some similarities top and bottom. To find the sum of a geometric series, use the formula S sub n equals the first term times 1 minus that common ratio raised to the n, not n minus 1 raised to the n, and then all over 1 minus r. No, the 1 minus r's do not cancel, not even close. You could lose one of them if that n was outside the parentheses, but definitely not in this form. So you're supposed to memorize this. And I'm thinking, do we have enough time to develop this? It's really close. I think we do. I think we do. So let's develop it. Now that you've got it written down, and here we go. So I'm just gonna put this on another page. So again, there's your formula. I'll even write it up here just to show what we're trying to achieve. So that's what we're trying to achieve. So here's the proof. And I'm gonna have to pause in a minute, but this will be really quickly. Let's just show what this sequence is, S sub n, which would be A1 plus A2 plus A3 plus A4 plus da-da-da-da-da-da-da, A sub n minus 1 plus A sub n. It's just the first through the nth terms. Now, each of these terms is something very specific, though. A1 is A1. A sub 2, we just showed with a previous formula, not the one you see on the screen, but just to find a specific term, is the first term times r raised to 1 less power. So that would be, if this is the second term, that means it's r to the first. And I will be explicit and write that 1 here. Plus, that means the third term would be the first term times r squared. The fourth term would be the first term times r cubed. The da-da-da-da-da-da I'll leave alone for a second. I'll give you a second to catch up. All right, but the da-da-da-da-da-da, I want to write these two things over here. So what's the n minus 1 term? Well, it's still a sub 1, the first term, times an r raised to one less than the term we're finding. This term is n minus 1. One less than n minus 1 is n minus 2. Because -1, -2. -2 is 1 less than -1. Plus the a sub n would be the first term times the r. Well, if that's the nth term, this is definitely n minus 1. All right, so there's s sub n. Now, this is just a trick. This is a trick that some mathematician figured out forever ago. Let's hold on to this thing. I'll do it as a blue asterisk. And now what I'm going to do is I'm going to take the above line and multiply both sides by r. By r. Why are we doing this? Because it just happens to work. How did some mathematician figure this out forever ago? Because they tried 10 billion things and this was the 10 billionth thing that actually worked. That's just how the real world works sometimes. That's how medicine works. You try 10 billion things until you find the thing that works, until you get your vaccine. Lots of failures in between, but we stand on the shoulders of giants and just take the one that works and forget the 10 million others that didn't work. All right, so we're taking r times s sub n. So every single one of these things is going to get an extra r. Every single one of them is going to get an extra r. So a sub 1 times r, because there's an extra r there now, then plus, and actually, let me see if I can do this. It's a pain, but I'll keep what was there before in black and what's new in red. So what was there before was black, what's new is red. So then plus a sub 1 r to the first times r plus a sub 1 r to the second times r plus a sub 1 r to the third times r plus da 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 a sub 1 r to the n minus 2. I said 2, but I wrote 1. There we go. Times r plus a sub 1 r to the n minus 1 times r. Now in blue, I will just show this whole thing condensed. So that's r s sub n equals a1r plus a1r squared, that's r times r, which is r squared, plus a sub 1 r cubed, r squared times r is r cubed, plus a sub 1 r to the 3, 1, 4, plus da 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 da. A sub 1, this is the next to last term, r to the n minus 2 times r. So this counts as an r to the first power. You're adding 1 to this. N minus 2 plus 1 is n minus 1. And plus a sub 1 times r to the n minus 1 times r to the first. Well, -1 and 1 cancel, so that's r to the n. Let's put an asterisk next to that thing. Now what we're going to do, this is the final step, well, next to last step arguably, is subtract the two asterisk equations. We're going to treat this like a system of equations. So we're just going to take these two things and subtract them. And admittedly, the order doesn't matter, but I'm going to do the first one minus the second one. So first minus the second. Now, the left side is this thing minus this thing. So again, I'll try and use colors, and this is going to become a pain in the butt, but I'm going to do it. S sub n minus r times s sub n equals. Now I'm going to actually do, how do I want to do this? How do I want to do this? Let's do all the black, then all the blue. So the black a sub 1 plus a sub 1 r plus a sub 1 r squared plus a sub 1 r cubed plus da 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 a sub 1 r to the n minus 2 plus a sub 1 times r to the n minus 1. Now I'm going to run out of room, unfortunately. Can I squeeze this? Ooh, that's not what I meant to do. That never works when I want it to work. Okay, forget it. Minus parentheses, I'm just going to put it down here. So then all the blue, a sub 1r minus, I'm sorry, plus a sub 1r squared plus a sub 1 r to the third plus a sub 1 r to the fourth plus da 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 a sub 1 r to the n minus 1 plus a sub 1 r to the n. So here's what happens. And again, it's the black thing minus the blue thing. Just pretend that the minus in the blue ink was all over there. These are all minuses. I'm not going to show the distribution because it just gets a little crazy, but that means all of these are negative. So this a sub 1 stays. This a sub 1r has a like term right here. A sub 1r minus a sub 1r. They cancel. This a sub 1r squared has a negative term here that it cancels. Minus a sub 1r squared. This a sub 1r cubed minus a sub 1r cubed cancels. That's what that mathematician hundreds of years ago recognized, that if they did this thing, they would have a ton of cancellations. All the da-da-da-da-da's cancel with the da-da-da-da-da. So even though I didn't write a sub 1 r to the fourth, that's in there, so it's gone. This a sub 1 r to the n minus 2 is the term before this blue one that's in the da-da-da-da-da, so that cancels. This a sub 1 r to the n minus 1 cancels this minus a sub 1 r to the n minus 1. And the only thing you're left with, and this could be infinitely many subtractions, the only thing you're left with is this term and this term, which also has a minus paired with it. So after all that, what we end up with is s sub n minus r s sub n equals a sub 1 minus a sub 1 to the, and then times r to the n. And now our goal here is to solve for s sub n, which we'll have to factor the left-hand side, LHS left-hand side, to do that. There's an s sub n in common, so we take it out. When we take it away from the first term, s sub n divided by s sub n is 1, then minus r s sub n divided by s sub n is r, and then that's equal to the a sub 1 minus a sub 1 r to the n. And then we just divide by the parentheses to solve for s sub n. Divide both sides by 1 minus r. And holy cow, you get the formula. Now you might say, that's not the formula. This was the formula. You have the a sub 1 factored out and with a parentheses. Well, you're right, we did. But that has a common factor, so you can factor it out. 1 minus r to the n over 1 minus r. Q, E, D. Quoterat demonstratum. Proof. Easy, right? Ha ha ha. This is a fascinating proof. I can't tell you how many times this came up in my math degree. How many times this type of thing was used over and over and over. Not always in the same manner, but you have this potentially infinitely many terms, or just a whole bunch of terms, and you need to get rid of most of them somehow. So you take an original thing, you multiply it by an extra thing, and then you subtract the two things to cancel most of the things. So it's a pretty awesome technique. And it's really hard to come up with on your own, but after you've seen it, you get to stand on the shoulders of giants, as we said, and it pushes you in the right direction for a lot of things. But again, what we're really going to be doing is just applying the formula. I don't really have a great way of memorizing this because there's no just logic to it. So let's try it out. Example 2, find the indicated sum. So the sum of the first 5 terms of 4 to the I. Now, I did not tell you it's geometric, so you can't just you can't just use the formula immediately unless you know. Now, after you've done dozens of these, you learn that, spoilers, this is a geometric form, but we need to actually show it by finding the first, second, and third terms, showing there's a common ratio, and then we can apply the formula. But Mr. Beckner, it's only 5 terms. Why don't I just do 4 to the first, 4 to the second, 4 to the third, 4 to the fourth, 4 to the fifth, and add them? Okay, true. But what if that was a 50? What was that, a 500, 5,000? Definitely don't want to do it that way. So first term is 4 to the first, which is 4. The second term is 4 squared, which is 16. Now we're trying to show that they're geometric, which means the ratio between them is always the same. So the so that ratio, 16 divided by 4, the second term divided by the first term is 4. So that should suggest that if this is a geometric, then each term is just 4 times the last term. But is that the R? Well, let's get the third term. 4 cubed is 64, and 64 divided by 16 is 4. Also, the third term is just the first term of 4 times 4 squared, which is 16 times 4, which is 64. So I showed it as the first term times r squared, or the second term times r. Those are both the same thing, just a matter of how many r's you're showing. And yeah, you just keep multiplying by 4, because each next term just means the exponent's going up by 1, which means there's an extra 4 multiplier. So that common ratio, that constant ratio, is 4. So you could turn this into a series or sequence where the next term is based on the previous term. So you could say that a sub n is a sub n minus 1 times 4. That would make it recursive. All right, so applying the formula, which I need to zoom out just a touch. The first term times 1 minus r to the n over 1 minus r. If we want to find the sum of the first 5 terms, that's the first term times 1 minus 4 to the 5th over 1 minus 4. Again, cookie cutter, just putting numbers into a formula. That's something you have to practice. The first term was 4, so that's 4 times 1 minus 5 to the 4. I could have gone straight to this. I don't know exactly why I chose to do it this way, and that's something you'll hardly ever hear me say. I don't know why I chose to put the r and the n in, but not the first term. It's fine. All right, 4 to the 5th is some big number. It's 1024. 1 minus 4 is negative 3. 1 minus 1024 is negative 1023. So that's 4 times negative 1023 over negative 3. Obviously, you're going to put that in a calculator. The negatives will cancel, and you'll get 1364. Geometric series can get really large really quick. They can, not always, it depends on the base. The bigger the base, the quicker it gets bigger. If you get a base less than 1, it actually gets smaller each time. We've addressed that marginally before. But it also means that something else could happen that we'll talk about. All right, let's try one more of these. Where's my B? That's weird. All right, well, that's fine. I can just put it over here. I know what it is. I have it in front of me. It's just not on my computer screen. The sum of the first 8 terms of 6 times 3 to the I. Now, again, I'm not telling you this is a geometric 6 times 3 to the I, not 3i. There we go. Big difference there. It wasn't geometric before that. Spoilers, this will be, but we still got to prove it. And that is something I would look for on your work. That I could, if I wanted to, take points off if you didn't establish that it's geometric. Now, you could certainly say, I know this is geometric based on the fact that I've done 100 of these, but I don't really think any of y'all are doing 100 of these before the test. So that's more for moving forward. For now, you need to establish, okay, well, what's the first term? A sub 1 is 6 times 3 to the first, which is 6 times 3, which is 18. The second term would be 6 times 3 to the second, which is 6 times 9, which is 54. If there is a common ratio, it would be the ratio of the second term to the first term. It's an ugly 2, but it is a 2. So that's 54 over 18. which is 3. So if the third term is 3 times the second term, then we're okay. So a sub 3 would be 6 times 3 to the third. 3 cubed is 27. And sorry, I thought I had that written down. 6 times 27 is 162. So if we take 162, oops, that looked weird. A sub 3 divided by a sub 2, it's 162 divided by 54. You get 3. So that's a second way of proving that it's a common ratio. The other way was you find is a sub 3 equal to a sub 1 times r squared, which would be 18 times 3 squared, which is 18 times 9, which, yes, it is most certainly 162. So r is equal to 3. That's our common ratio, our constant ratio, whichever C word you want to use. So the sum of the first 8 terms of this geometric series. And see, when I use this S, is it arithmetic? Is it geometric? I don't know. You have to say somewhere or prove somewhere that it's the R or the D. When I use the letter R, that means it's geometric. If I use the letter D, it means it's arithmetic. But the formula we use is the first term times 1 minus R raised to the 8th all over 1 minus R, where the first term was 18, the R is 3. See, last time I didn't put I put the 3 here instead of an R. That's what I was trying to say earlier. I don't know why I didn't write that last one with R's. I already put the number in. It's arbitrary, but not the end of the world. 3 to the 8th is some big number. It's 6561, so that's 18 times 1 minus 6561. 1 minus 3 is negative 2. So if you subtract 1 and 6561, you're going to get negative 6550. I'm 6560, excuse me. I don't know why I said 50. All over negative 2. The negatives cancel. Half of 18 is 9, so you're just doing 9 times 6560, which ends up being 59,040. It's a pretty large value for just a sum of first 8 terms. But as we said, sequences and series can get large quick. They don't always, as we'll start seeing very shortly. Yeah, we're going to have just enough time to finish. I'll leave that up there for about another 30 seconds, and then we're going to go back to the other page. I think this was an instance where Word, when I was writing my notes, crashed, and it didn't save the last instance. And I just missed the fact that it deleted B, and I kept moving forward when I wrote my notes. It's happened to me a few times. All right. So, actually, I'm missing a whole bunch of stuff. Wait, what? Why is it down here? What happened? Why are those here? All right, it got even weirder than I thought. There's B. My pages are out of order. I don't even know how that happened. All right, Word, everybody. Word is an awesome program. And they don't even pay me to say that sarcastically. So there's B. We'll scroll back up to this in a minute, since I'm assuming it's not going to be down here. And, oh, hey, wait, and there's the proof that I was talking about earlier. I'm sorry, everyone. That's just silly. Okay, doesn't matter. So let's try to find an infinite sum for the first time. This is heavy, heavy calculus right here. Calculus, Calc 2 specifically, you get into all these infinite series, an infinite sum. And specifically, we like infinite series when they're geometric, when there's a constant multiplier. And we can actually find a geometric sum if the constant multiplier in absolute is less than 1. So it can be positive or it can be negative, but it has to be smaller than 1. And this is a very basic idea because if it's bigger than 1, let's say you just start out with the number 1. Let's say the r is 2. So the next number would be 2, then 4, then 8, then 16. And it would just keep getting bigger and bigger and bigger. Even if your r is 1.01, you'll go to 1.01, then 1.0, whatever, but it will keep getting bigger and bigger and bigger. If your r is less than 1, say like a half, if you start at 1, you multiply and you get a half, then you get a quarter, then you get an eighth, then you get a 16th, then you get a 32nd. You get this asymptotic behavior like we saw back in pre-calc 1 where things start going to 0. So when you require that constant ratio to be less than 1 in absolute, it will make the nth term head towards 0 as you get really, really, really large in your number of terms. It never actually becomes 0. It's going to become 1 millionth or 1 billionth or 1 trillionth or 1 quintillionth, etc. as your n goes to a million or a billion or a trillion, whatever. So it never actually becomes 0, but these numbers, these terms become so small that it's possible that when you add them all up, you actually get a finite answer. So if your nth term is going to 0, your nth term is basically just some a1 times r to an exponent, and the r to an exponent is going to go to 0 because this is like 0.05 times 0.05 times 0.05 times 0.05 times 0.05. Oops, I should turn my calculator on, shouldn't I? And clear it so we don't get confused. So if you just keep multiplying by 0.05, there's after your first one, here's after your second one, here's after your third one. It's already getting tiny. Negative exponent, tiny. Multiply again. Tinier. Multiply again. Tinier. Multiply again. The more I multiply by a number less than 1, oops, I forgot the times, but you get the idea. It just keeps getting smaller and smaller. So in R, a number raised to an exponent where that base is less than 1 is going to go to 0 as n goes to infinity. This is the type of stuff you really start studying in calculus. Asymptotic behavior, especially trying to get things to go towards 0, or at least a number that's whole, 5, 2, 3, -1, whatever. So what we're going to do is we're going to take that previous formula, so there's nothing new written at the bottom, but now let's imagine that the n is going to infinity and the r is less than 1. So if your r is less than 1, this thing right here is going to go to 0. This right here is going to turn into 0 as your n becomes infinity. As we just said, a number less than 1 in absolute raised to an exponent as you keep multiplying over and over and over and over and over, it just keeps getting more and more and more and more small. It eventually goes to 0. So when you're actually in the infinity state, it literally becomes 0. So that's what we see here. Sorry for the little scribbling there. You can't see most of it anyways. Nothing else changes. The first term doesn't change. The r doesn't change. It's not the r going to 0. It's r to the n going to 0. The r is still just that r, that 0.5 or whatever number it might be. Well, on the top, 1 minus 0 is 1. A sub 1 times 1 is a sub 1. I'm missing a 1 here. Not a big deal. Red, you silly goose. So we can actually find an infinite sum of terms based on this arguably simpler formula. The finite sum is, in my opinion, more complicated than the infinite sum. The infinite sum is just take the first term and divide by 1 minus r. That's it. It's probably the most ironic thing in trigonometry. And this isn't even trigonometry, just in the class where we're taught trigonometry. Math analysis, if you're in high school, is where we learn this usually. So this formula works for a geometric series only, and only if your constant multiplier is less than 1 in absolute. So it can be negative, it can be positive, so you can have an alternating sequence or series, but the multiplier itself in absolute has to be smaller than 1 so that those numbers aren't blowing up over time, either in the positive direction or the negative direction or an alternating fashion. So another formula for you to memorize, arguably easier, but you do have to memorize it. All right, got just enough time to rock these two examples and we'll call it a day. Which, that's right, they're up here. And I'll put the formula up here. S sub infinity is the first term over 1 minus r. That's the formula we use as long as constant multiplier, constant ratio is less than 1 in absolute. And Mr. Beckner, you didn't even write this out in a series format. You're right, I didn't. Because quite often they're not. This means you have to establish what the first term is. It means you have to establish what the r is. And that it's less than 1 in absolute, and that you can apply the formula. So 1 plus a third plus a ninth plus a 27th plus an 81st plus a, what's that, 1 over 243 plus yada, yada, yada. And I say go forever and ever. So we keep adding smaller and smaller numbers. So the further we go, the less effect it has on the sum. And believe it or not, you can actually have series where this sum goes forever and the terms are getting smaller, but it diverges. It actually doesn't go to a finite number. It just keeps getting bigger and bigger and bigger. You'll study that in calculus though. All right. So what's our first term? Well, our first term is very obviously 1. Our first term is 1. What's the second term? Well, it's very obviously 1/3. What's the ratio of these two things? A2, if it's geometric, then the r is the ratio of the A2 to A1, which is a third divided by 1. Anything divided by 1 is itself, so that's a third. Now that's if it's geometric. To prove it's geometric, we take the second term, we multiply it by what we think is the r, and see if we get the next term. And certainly 1/3 times 1/3 is 1/9. So the third term is labeled up here as 1/9. If we take the second term times what we presume is the r, that's a third times a third, which is also 1/9. So it is geometric. Now, since it's geometric and the r is less than 1 in absolute, we can apply the infinite sum formula. If the r was, say, 3 instead of 1/3, this is an infinite sum. It goes to infinity. We keep adding bigger and bigger and bigger numbers. But here we're adding smaller and smaller and smaller numbers, and it happens that we can add these up. So we apply the formula, we take the first term and divide by 1 minus r. The first term was 1. The r is a third, so 1 over 1 minus a third. Oh man, fractions inside of fractions. Mr. Beckner, I was hoping these never came up again. Yeah, that's the thing about hoping. Doesn't always happen. Told you it never goes away. So I would suggest getting an LCD between all the denominators. The only denominator you see is a 3. So I'm going to multiply everything by 3, as you can see here. Pretend like I didn't cancel those out yet. Pretend like I actually clicked eraser. Word. Go. So 3 times the 1 in the top, 3 times the 1 in the bottom, 3 times 1/3 in the bottom. We do that so that these cancel. There's no more independent fractions. It's just 3 over 3 minus 1. 3 minus 1 in the bottom is 2, so 3 over 2. 3/2, also known as 1.5. I love this problem because look at how small that number is, 1.5. Look at what the first number is, 1. we are already almost at the infinite sum by the first term. If we keep adding these infinitely many numbers, a third plus a ninth plus a 27th, all of that just turns into a half. That first term is the biggest chunk of the sum. If you add the first couple terms, 1 plus 1/3, 1.333. We're only 0.166666 away from the infinite sum by the time we hit the second term. If we add the next term, which is plus 1/9, now we're only 0.55555 away. I'm sorry, 0.055555 away. We are so freaking close to what it actually represents by the third term of the sequence. And if you remember, at the beginning of this chapter, I had said that in calculus, one of our goals is to turn kooky functions like sine and cosine, which we can't just crunch numbers by hand with, into polynomials, infinite sums of polynomials, but where you really only need the first couple terms of them, because by the time you're at the second or third, most of the time, you're pretty much at what it really represents. Is it that big a deal if we're 0.05 away? It depends on the scenario. And that's where we start getting into error ratio arguments, error propagation, all that stuff. All right. So again, just the point of this is, you really, in these infinite sequences and series that converge, by the second or third or maybe fourth terms, you usually pretty much have the approximate value. It's an approximation. It's not exact, but it's approximation. If you use all 10 quintillion of them, then you get it exact. But again, in computational math, what a lot of people like to do is take crazy exponential sine, cosine functions, things you just can't crunch by hand, turn them into just a couple polynomial terms that approximate within a window, and boom, you're good enough to go. All right. Last problem of the section, last problem of the chapter, B. Two minus 1 plus a half minus a fourth plus an eighth plus yada, 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 yada. So that would be minus 1/16 plus 1/32 minus 1/64 plus 1/128. Each of these numbers just keeps halving, but they also change sign, whereas in A, they kept decreasing by a third each time. So B, not only are the values getting smaller in absolute, but they're also alternating. And if they're alternating, that means that the R is negative because you're multiplying by -1/2 each time, spoiler alert. How do we show that we're multiplying by -1/2 each time? You find the first term, you find the second term, you divide them, you find the third term and make sure that it works in that pattern. The first and second terms are already clearly labeled. I did not give you formulas to plug in. I could certainly give you formulas to plug in. I could certainly have made the problem look like this instead, the sum of the first to the infinite term of, what was it, 2 times a half, -1/2 raised to the I. I think that would be the formula. So I could have given it this way, and then you have to plug I equals 1 in to find A1, plug 2 in to find A2, plug 3 in to find A3, do those ratios, et cetera, et cetera. All right, first term is 2, second term is -1, divide them. Make sure you do the second divided by the first. So if it's geometric, then that R would be the second divided by the first, which is -1 divided by 2, which is, well, very obviously -1/2. So if the third term divided by the second term is -1/2, or if the third term is the second term times -1/2, both of those arguments work, then you're good. Well, we can see that the third term is exactly 1/2, +1/2. So is the third term the second term times R? Well, the second term is -1, the R is -1/2. -1 times -1/2 is +1/2. Or you could have done 1/2 divided by -1, which is -1/2. Again, you could just do A3 divided by A2. That's another way of showing the work. So yes, this is geometric, with the R being -1/2 and the first term being 2. And again, me writing out the numbers that way is exactly the same as if I'd written it this way, the sum of the first through the infinite terms of 2 times negative 1/2 raised to the I. That's the same thing. I plus 1, I minus 1. It's close. Hold on. The first term should be 2, so I minus 1. I just want to fix that. It's actually that. That way, if you plug in 1, the negative 1/2 will be raised to the 0, and it spits out your 2, and then it just keeps halving each time. All right. So the infinite sum, using that formula, it's the first term divided by 1 minus r. It doesn't have that extra 1 minus r to the n. That's actually the convenience between the finite sum and the infinite sum of geometric sequence and series, because they're very similar. The infinite sum, you just cut out the 1 minus r to the n. I think the infinite sum makes the finite sum easier to remember because you get a twofer, basically. So the first term is 2. The r is negative 1/2, so you get a double negative situation going on. 1 minus negative 1/2, which is 2 over 1 plus 1/2. LCD that bad boy. The only individual denominator we see is this 2. So all the bits get multiplied by 2. Pretend like you don't see the lines crossing out quite yet. There we go. So we're here, 2 times 2, 2 times 1, 2 times 1/2. These 2's cancel, so you just get 4 in the top. The 2 times the 1 here is this 2. With these 2 canceling, you're left with just the 1. 2 plus 1 is 3, and the answer is 4/3. 4/3 being 1.33333333. 33333. So check this out. Let's just add some of these numbers. And, well, I mean, the first number is 2. 2 is pretty close to 4/3. I mean, it's 0.6 off roughly, 0.66666. So it's in the ballpark. It's not too exact, so I don't know that one term is good enough. All right, well, maybe we just use the first 2 terms, 2 minus 1. That's a little closer to 1.3, but it's still 0.3333 off. So it's good, but it's not great. Well, let's put in the 1/2. So let's add a 1/2. Now we're at 1.5. Now, the previous problem, we were slowly gaining to that value. This time, we're kind of dancing around it. We're dancing around that 1.333333. We start at 2 on the right, then we're at 1 on the left. Now we're at 1.5 on the right. I bet the next time, when we subtract a quarter, we're going to be to the left of 1.333, and we are. But each time, even though we're oscillating, with each oscillation, we're getting closer and closer and closer. So now by the time we get to the first, second, third, fourth term, 1.25 is pretty close to 1.33. Depending on the scenario, maybe it's good enough, or maybe we need the next term. Maybe we need the next 2 terms. But when I add an 1/8, now we're only 0.04-ish away. When I subtract the 1/16, now we're only like 0.02 away. We keep getting closer and closer. We are converging to this value. And again, in terms of applications in computational math, maybe we only need to be within like a 2% error ballpark, and maybe we're in that 2% now. We're actually a little better than 2% in fact. You know, what kind of error is acceptable? 1% error, is that okay? 5% error, is that okay? 0.1% error, is that okay? Depends on the application. All right, so that is chapter 11. So next week, what we'll do is we'll talk about chapter 10 a little. We won't finish it. I might only kind of brief it as a concept, and then we'll see what we're going to do after that. I know Monday we'll talk about chapter 10. It's a matter of what we do on Wednesday. But remember that next week we have a test. So a week from today, where did I write that? Did I put it on this one? I did not. Did I put it on this one? I must have deleted it. Either way, you saw it at the beginning of class. You know what the expectations for test 3 are a week from today, as well as that Thursday. I will have the review up no later than Monday. I will try and get it up tomorrow. Actually, no, I'm sorry. I already have it up. What am I talking about? I already have it up. I'm hungry, if you can't tell. Sorry. So yes, the review is already up, so go ahead and start working on that in addition to getting your homework. But 11.2 and 11.3 will be due 1 week from today. So if you have any questions, please email me. Besides that, have a good day, have a good weekend. We're at the finish line, so keep working strong, and we'll see you on Monday. Take care.